Alright, new problem. So, I have this ugly square root in this problem. Now you might look at this and say, well, trig substitution's not going to help us. It doesn't look like any of the problems we've done. Well, it turns out we can still do a trig substitution. So the goal is we want to take this stuff in here and we want to make it look like something squared plus 1 or something squared minus 1 or 1 minus something squared. We have a method for doing this. So we need a method for taking a quadratic here and rewriting it as something squared plus a number or something squared minus a number. That's completing the square. If we just do completing the square on this guy, we'll have something that we can do a trig substitution with. So the algebra on this problem is the hard part. Say, okay, I'm going to take this guy and I'm going to complete the square on it. So first things first, if I'm completing the square, I got to get rid of that leading coefficient. It messes everything up. So I'm going to factor out a 2. So I got x squared minus 6x plus 14. All right, so I just ignore that 2. That's just hanging out there. So if I'm completing the square, the process is, well, I'm going to take half of that number. So I'm going to take negative 6, take half of it. So 1/2 of negative 6 is negative 3. And then what I'm going to do is take that number and square it. Negative 3 squared is 9. So 9 is the magic number that I'll be adding and subtracting to help me complete the square. So I'm going to have x squared minus 6x plus 9 minus 9 plus 14. Now why was this okay to do? Well, 9 minus 9 is 0. So if I add 9 and subtract 9, I really just threw in a 0 there. Well, that's fine. I can add 0. Okay. So what was the whole point to all that? Well, this chunk here, this factors. This factors as x minus 3 times x minus 3. Negative 9 plus 14. That's 5. So now I got 2 times x minus 3 squared plus 5. Aha! So if I complete the square, that's what I'll end up with. I can, if I want, I can distribute that 2. So I got 2 times x minus 3 squared plus 10. I can do that if I want. Anyway, so all right, go back to our original problem here. I can replace all that stuff. I can replace it with 2 times x minus 3 squared plus 10. All right, I'll look at my trig identities and I say, what does this most look like? Well, I got something squared, some stuff squared plus a number. Okay, it's starting to look like this guy, something squared plus 1. Still doesn't look quite like it. I don't have a 1. So all right, I can get a 1. I'll factor out a 10. Put a 10 here, and if I do that, all right, well, I better put a 10 here. Like so. Okay. And now, all right, having that 10 under the square root's a little annoying, so I'll just pull that out. So I got square root of 10 there. I got this other stuff inside. So 2 divided by 10 is 1/5. So I got 1/5 x minus 3 squared plus 1. All right, so this is starting to look a lot more like something squared plus 1. It's still not quite there yet. The reason is this darn 1/5 here. I don't have one group of stuff squared. I got a number times something squared, so I got to change that. So what I got to do is I got to rewrite this as x minus 3 over root 5 squared. That'll work. If I square what's in parentheses, I will have x minus 3 squared. If I square the square root of 5, I will have, it'll make that 5 in the denominator. Then I have plus 1. All right. Great. Now finally, I can say, okay, this now looks like something squared plus 1. I want to let all this stuff be my tangent of theta. So I'm going to have x minus 3 all over the square root of 5. That equals the tangent of theta. So I can say x minus 3 equals root 5 tangent of theta. So x equals root 5 tangent of theta plus 3. All right. I take derivatives. Dx d theta is equal to root 5. All right, derivative of tangent, secant squared theta. Derivative of 3 is 0, so that's pretty boring. All right, that guy's gone. So dx equals root 5 secant squared theta d theta. All right, so I replace stuff in my integral now. So let's see here. I got this root 10 sitting out there. And then I'm replacing x minus 3 over root 5. I'm replacing that with tangent of theta. So I have tangent of theta squared plus 1 d theta, or dx, I'm replacing that with root 5 times secant squared theta d theta. Now it's just a matter of simplifying. So root 5 on top, root 10 on the bottom. Well, I can actually simplify that root 10 as root 5 times root 2. So I can cross off those root 5s. Tangent squared plus 1, that's secant squared. All right, cross off those root 5s. I got secant squared theta d theta all over the square root of 2 times, all right, square root of secant squared is absolute value of secant. But we saw earlier, well, you know what? We don't need the absolute values. We talked about that in, I guess, the third video, I believe. Turns out we can get rid of those absolute value bars. We might as well just ignore them. We can cross off secants. So we have to find the antiderivatives of 1 over root 2 secant of theta d theta. Now the antiderivatives of secant of theta, they're a pain. So I don't like doing this, but this is one of those situations where I say, you know what, you just want to memorize the antiderivative of secant theta. Antiderivative of secant theta would be natural log of secant theta plus tangent theta, absolute values. It's just a good one to know. So, all right. Now, I'm almost done-ish. So, my original problem had x's in it. I need my final answer to have x's in it. So, let's see here. So I'm going to have to use the triangle trick. I let x minus 3 over the square root of 5. I let that be the tangent of theta. So there's my opposite side, and there's my adjacent side. So if I draw a triangle here, all right, there's my triangle, theta. Opposite side is x minus 3. Adjacent side is root 5. Hypotenuse is the square root of x minus 3 squared plus root 5 squared, which is 5. So there's the hypotenuse of my triangle. So if I want the secant of theta, it is hypotenuse over adjacent. If I want the tangent of theta, well, I guess we already know the tangent of theta. It's x minus 3 over root 5. Great, so I take secant, I replace it with this whole mess. I take tangent, replace it with that, and I'll be done. So I have 1 over the square root of 2, natural log, absolute value, square root x minus 3 squared plus 5 all over the square root of 5 plus tangent to theta, x minus 3 all over square root of 5 plus c. And now that's about as messy as they get. So, completing the square. If you forgot it, practice it. There's practice problems up online. They're optional, but if you forgot how to do this, you should do that optional assignment. The other thing is, all right, again, this problem was a mess. Completing the square on this guy made this problem a huge algebraic nightmare. If you do this problem using my method, or I take the stuff under the square root and I make it look like something squared plus a number or something squared minus a number, the trig substitution part is actually not that bad. That's actually the least confusing part. You just say, okay, I got that something there. Well, in this case, I'm going to replace this whole something with tangent to theta. The book's method, where you just kind of memorize and say, okay, when I'm in this situation, I let this stuff be tangent to theta. It's kind of harder. I mean, my method, the reason why I like my method better for trig substitution is for difficult cases like this. And there are some scenarios where this trick, again, applies to other situations where it's helpful. So anyway, like I said, there is a reason why I do my trig substitutions this way, even though it takes a little extra writing.